This project was initiated with the goal of generating a proposal for ephemeral architecture on a 20 by 20 meter plot within the Humanities Zone of UTLA. The process was characterized by an evolution of the structural concept based on an analysis of constructive feasibility. The Foresta Pavilion is conceived as a grand architectural tree, whose structural function translates into a sensory experience. Its columns simulate strong trunks supporting a roof that represents a wide arboreal canopy. This roofing is key, as its strategic voids and geometries filter sunlight, creating dynamic shadows on the ground, replicating the sensation of being under the foliage of a forest. The initial stage consisted of a topographic and spatial survey of the area to determine the site conditions. The 20 by 20 meter limit was defined, which serves as the framework for the design of the plans and elevations of the first conceptualization. This phase established the geometric and functional basis of the space. For the formwork model materials, balsa wood and battery paperboard, were primarily used. The choice of these materials was based on their ability to precisely represent the temporary structural elements of the system with geometric accuracy and low self-weight. The model was rigorously developed maintaining a 1:25 scale, respecting the real dimensions and proportions of the structural design. Once the dimensions were defined at scale, the pieces were traced onto the balsa wood. Subsequently, precise cutting of the wood was carried out using a utility knife cutter to ensure the dimensions. These elements form the essential components of the formwork, which include stringer beams, vigas madrinas, the main longitudinal structural elements that receive the load, ledgers or joists, lines, intermediate transverse elements that directly support the sheeting planking, and bracing, contraventeos, fundamental diagonal pieces to confer lateral rigidity and volumetric stability to the temporary structure, preventing buckling or collapse. The parts were assembled using temporary mechanical joints, pins, or tacks. This method was chosen to guarantee the structural stability of the assembly before the placement of the contact surface. The next technical step consisted of placing the battery paper, which served to simulate the contact surface or sheeting. This material was cut to the exact measurements of the surface to be molded and carefully fixed onto the balsa wood frame. Finally, general quality and resistance checks were carried out to verify the structural integrity of the model, ensuring its capacity to simulate the loads and geometries of the definitive constructive element. The development experienced a redesign. The primary design faced a fundamental obstacle during the review of its constructive feasibility. The initial proposal, which presumably involved a complex roof or geometry, required an excessive number of point supports. This high density of vertical supports compromised the functionality of the interior space, limiting circulation and flexibility, and the aesthetic clarity of the ephemeral design. Therefore, it was determined that the original design of the formwork, understood here as the structural system supporting the roof, had to be discarded. To solve the problem of point supports and maintain the architectural vision of a sloped roof, the strategic decision was made to integrate trusses as the main structural system for the roof. The truss is a reticular system that transforms gravitational loads into pure axial forces, compression and tension, and its members maximizing material efficiency. This allows for spanning large distances between supports with a reduced structural weight and, crucially, significantly reducing the number of necessary vertical supports. Once the truss-based structure was conceptualized, the detailing of constructive plans for precise fabrication proceeded, opting for lazy cutting to guarantee the zero-dimensional tolerance required at the connection nodes. With the main trusses defined and conceptually installed, the design advanced towards the roofing and enclosures. A new critical error was detected when attempting to integrate a curved structure into the roof. This form lacked the adequate lateral rigidity or bracing, which risked the overall stability of the roof. To solve this instability and ensure the underformability of the roof plane, a lattice or reticular framework was incorporated. The lattice functions as a rigid diaphragm that distributes horizontal loads, such as simulated wind or seismic forces, towards the main supports. This same bracing resource was replicated in the perimeter skirt walls. Finally, the L-shaped walls with their respective internal frames were designed, which not only define the space but also contribute to the general rigidity of the structural box. The final phase of the design incorporated functionality and habitability elements, including service installations, design of the LED lighting circuits, low voltage and efficiency, and hydraulic installation, simulation of supply and drainage points. Also, it includes furniture, definition of the internal arrangement, which reaffirmed the importance of the open plan space achieved by the trusses. In conclusion, the development of this project demonstrated the high utility of scale modeling as a validation tool in architectural design. The 1/25 scale simulation was crucial as it facilitated the identification and practical understanding of the specific function of each structural component in the ephemeral context of the pavilion. This process allowed for an effective assimilation of the construction methods for each element, integrating them into a logical and rigorous assembly sequence. From a resource management perspective, it is concluded that the detailed analysis of the physical modeling directly contributes to the precise quantification and effective optimization of materials, minimizing potential waste. Furthermore, a deep understanding of the model's structural functioning was fundamental, making the elaboration and assembly of the complete model simpler and more effective. Regarding methodological recommendations for the future projects, it is highlighted that working with an adequate scale is fundamental, as it considerably facilitates the development and manipulation of the model details. Likewise, the implementation of high-precision technology, such as laser cutting, proved essential to drastically optimize production times and guarantee the dimensional accuracy of the components. Finally, to ensure constructive integrity, it is recommended to methodologically elaborate the model assembly, using the pertinent tools correctly. This systematic approach not only facilitates the pavilion assembly process, but is vital for preventing structural problems or unnecessary material waste.